Okay, so what are vanadium flow batteries? So vanadium is an element. In the lab, we get it as this beautiful crystal blue powder form. It's absolutely shiny and sparkly. Please don't eat it. Like, oh, Jesus Christ. Do you know how tempted I was to try to eat this? It's amazing. But yeah, I never did so. There's no odor or smell from it, and it comes in this blue form because of the water in the powder. Usually most powders in chemistry are all white, but it's the water molecule attached to the powder that makes it this colorful color. And this form is VOSO4, and it is in the fourth oxidation state. That's why it's such a beautiful blue color. And what we do with this crystal blue powder form is that we dilute it into electrolyte using acid and water. The acid we use is sulfuric acid, H2SO4. And when we make it into solution for a battery, we make it in 1.5 molar vanadium in 4.5 molar SO4. Now, the reason why I said it this way, you might say that's a weird way of saying it, 1.5 molar vanadium, 4.5. Why use this combination of words? Well, first of all, there's two compounds in there. There's vanadium and there's H2SO4, sulfuric acid. But there is inherently vanadium attached, there is inherently SO4 attached to the vanadium powder. And on top of that, as the vanadium changes into different electric states, V5, V4, V3, and V2, which I'll talk about in a minute, as it changes from those forms, the concentration of pure H2SO4, the concentration of sulfuric acid changes actually. So it would be lying if I said that it was 4.5 molar H2SO4, because that's only in vanadium 4. When it changes to other oxidation states, that value changes. So that I don't lie, I formatted it in this sentence: 1.5 molar vanadium and 4.5 molar total SO4. Because the total SO4 doesn't change. And then vanadium can exist in 4 oxidation states: V5, V4, V3, V2. And they're beautiful colors. As you can see, they're in the photo. But in person, you can see this. This is vanadium 5. It's precipitated. That's why it's red in color here. And V4, beautiful blue color. You can't really see on the camera, but that V3 is bright AF. And that V2 is so purple, it's blinding. But the camera just can't seem to capture that purple color. It's absolutely a wonderful color. Now, the way the vanadium flow battery works is that you have V5 and V4 on the positive hand side of the cell, and you have V3 and V2 on the negative hand side of the cell. And so what happens is when the battery is discharged, you know, when your phone battery is 0%, the V4 is on the positive side and the V3 is on the negative side. Now, when your battery starts to charge, your phone, for example, from 0% to 100%, the V4 on the positive side changes to V5, and the V3 on the negative side changes completely to V2. And that is the cycle of charge and discharge in a vanadium flow battery. It changes from V4 to V5 on the positive and changes from V3 to V2 on the negative, and back and forth. It's a rechargeable battery. And that's a beautiful photo just to show it charging over time. And you can see the purple color, the yellow of V5, the blue of V4, and the green of V3. Now it looks very dark here because it's condensed. The photos I took here are very low concentration solutions of vanadium. In reality, V5 wouldn't even be yellow. It's actually brick red blood color. It's very, very deep. It's just because the concentration of vanadium is here very low, just for the sake of photos. So just for the sake of a pretty picture, that's why everything is the way it is. And finally, there's actually a lot of batteries being used around the world. Japan, China, America. A lot of countries like that have been using them for a long time as experimental and offload systems, similar to like how flywheels have been installed a lot. But just last year, actually, Dalian in China built the largest vanadium flow battery infrastructure, which I also saved as an article we can talk about in the end. It's really cool. It's one of the largest infrastructures that exist, and we'll talk about a little bit about that in a while. So here is a representation a little bit of how a vanadium flow battery works. You have V4, that's the discharge state. You have V4 on the positive hand side, and you have V3 on the negative hand side. You have sulfuric acid, HSO4, and you have water charged molecules, H3O plus, and protons. Of course, this is how it tends to look in its discharge states. And they're just chilling in the liquid. They're having a lot of fun and having some good crack while they're mixing up together like this. What would be the primary use for vanadium flow batteries when compared to other? So because they're so large, Daxter, they would be used specifically for grid integration, to storing excess energy during excess energy production, i.e. high winds in Ireland. So when there's a lot of wind in Ireland, that's when we'd be using them. So let's look a little closely at what happens when you start charging a vanadium flow battery. So you have V3 on the negative hand side and you V4 on the positive hand side. So we start charging, okay? So what actually happens is the V4 changes to V5 in the process, producing an electron, which travels around the circuit, completing the circuit, and 2 protons are produced, increasing the conductivity of the electrolyte on each side. Now, to make sure the electron goes into the V3, changes it from V3 to V2. And to balance this whole reaction, the proton has to transfer across the membrane. That's what this grey line here is. It's a cation exchange membrane, which means it allows positive charged particles to pass through. And that's how the proton travels through. If you look at it from an equation perspective, I'll show it to you in a second, it's completely balanced. So what happens is this is the flow battery in its discharge state, and you begin to charge it. And this is the colours that change to purple on the negative hand side and lovely red color on the positive hand side to V5. Like I said earlier, you can represent the equations on each half cell in a electrochemical equation. I won't go into it into too much depth. You're either familiar with chemistry equations or you're not, so I don't want to hassle you too much. But this would be the formula or representation of the different vanadium oxidation states in their chemical formula. So in red we have VO2+, in blue we have vanadium 4 with VO2+, different 2+. V3 is just V3+, and V2 is just V2+. So at least the negative side isn't too hard to be familiar with, and that's their electropotential value respectively. So yeah, that is the introduction of my vanadium flow batteries to my PhD defense, and I think it explains how vanadium flow batteries work pretty well. The rest is my chapters and my research that I won't be able to go through.